So in case of just a minute. So in case of the transmission line theory, which is actually the last two sections of the course, we have actually this very important one, because the one of the important application of electromagnetic field theory is the transmission line theory, where we are going to study how this wave travels inside wire, and how communication is reasonably connected with that. And not only that, many important aspects are connected with this particular theory. So we will study about that, so that you can even understand that how to describe the wireless communication as well, where the antenna theory will come into the picture. And we have also seen that how this transmission line theory is connected with microengineering, which are very important topics of electronics and communication theory. So we will go much more in detail, and today we are going to talk about this transmission line equations, and then the primary and secondary constants, so that we can express these constants as a impedance, which we call wave impedance or characteristics impedance. By the way, we can understand how this wave propagation mechanism takes place inside a transmission line. This is completely different theory so far now what we have learned. So this wave theory, which we already discussed over the course of time, will be very helpful to understand the transmission line theory. But you need not to afraid of that. These sort of equations won't come in the near future. So most probably we will solve everything with the RLC equivalence. So it will be very easy to solve most of the transmission line theories with simple equations, and as well as humble equations. So we have seen that how this wave travels in a medium, and how to define the wave, all these things. So one of the important thing you have to understand, these theoretical equations are telling about the descriptions of the wave propagation possibilities, and there are n number of possible way the wave can propagate inside a medium, and so which we call harmonics, and time as well as frequency harmonics, like that. So as well as in terms of space also, how this propagation takes place. So it is purely depends on how we excite the so called the wave. For instance, you have a metallic box completely surrounded by metal. We know that the electromagnetic wave cannot escape out of the box, but within that scope, how the wave can propagate inside that. And indeed, within the scope of the space, the energy is stored. So when the energy is stored, there are two possible energies, electric and magnetic. So by the way, the box can be having equivalence of a capacitor and inductor. And when the walls are completely lossless material, let's say pure or perfect conductor, then there is no resistance at all. So this is completely going to store the entire structure, entire electromagnetic energy. So uh, there are so many possible things you're supposed to understand, that if this is the box, the way we excite, when we give the signal, when we give the electromagnetic wave from here, from the center, from this edge, or from this corner, like that. So there are so many possible way the wave can propagate inside. I believe all of you can understand that. So this is what you have to keep in mind when you understand, when you try to understand the wave equations of a given electromagnetic material. So there are so many descriptions we have seen, and as well as calculation of power, all these things. So this all theory we are going to apply into a transmission line, and of course the waveguides. So these are the two possible guiding medias or guided medias. So guided media is nothing but this medium is going to make the wave to travel in a particular fashion in a given along a particular direction. If it is a infinite boundary, which means there is no boundary at all, then wave can travel in almost all the directions. There are about n number of possible ways will come. But if you try to mention the boundary, then the limited scope of propagation alone will be there. that propagation sometimes help to control the overall behavior. For instance, because of that only we can say that the secure communication takes place. And once you have been inside the transmission line, there will be two boundaries will be there. This two boundaries, one is conductor, another one is going to be ground. And there are some waveguide phenomena where you can't distinguish the one positive, negative, like that. Actually, sometimes you can't distinguish, but within the propagation, you can easily understand that. So one is actually going to be positive and negative, like that. So even though there is no perfect positive negative like this kind of metallic structures, this naturally will happen within that, and that makes the different shapes of field distributions, which we call modes. There are three possible modes: TEM mode and TE mode, TM mode. I believe we already studied about that much more in detail. Those who are willing to do it, you can see the last lecture recording. So what is the general thing we supposed to keep in mind when we consider this TEM wave as well as TE or TM wave is the limitations of the propagation. So for this, we have taken a simple example of a parallel waveguide as well as four-sided waveguides as well as a transmission line. All these things, when we see that the propagation can be defined in terms of certain parameters, which we call the phase constant, attenuation constant, or propagation constant, which are often referred as primary constants. And thereby we can see how this behavior of different distributions can be understood. So this can be applied to real-time transmission lines like waveguides all the way, and where we can see different what are the behaviors it can allow. Okay, so these kind of allowing behaviors, we call them as the modes. For instance, if you take a rectangular waveguide where the wave propagation takes place in this, but if you take any particular point, you take a section and see the distribution, you will see either this distribution like that. So there actually TEM mode cannot exist. Okay, so only TE mode or TM mode can exist. For instance, the first three modes are TE mode and fourth mode is TM mode, like that. And so for this, what we have to do, we have to apply the Maxwell's equations. We have to self-consistently solve the equations. It is not a big deal. Simply you have to differentiate this equation and substitute the equation on another. Then you will get a second derivative of the del vector. So obviously, which is going to give second order equation that has two solutions. One is positive going and another one is reverse going signal. That is wave equation. That wave equation, we are going to apply the boundary. Then we can see limited number of waves that can propagate within the scope of the waveguide or any transmission line. And there comes new parameters, which is very similar to that of the wave equations, which already have discussed. We have also seen that how the propagation constant as well as attenuation constant available in a waveguide. So we will really understand the meaning when we apply into the application. These are the things we have so far now discussed. Now we are going to the exact transmission line theory. So far now, whatever that we have dealt, it is just an introduction. You need not to fear about if you can't understand. So you need not even understand that, because these are simply the introductory theories for the transmission line. Okay. So in case of transmission line theory, first you have to visualize what are the types of transmission line that is possible for various applications. Particularly when the high frequency signal comes into the picture, they have, for example, if you take the very low frequency like voice and all, it can simply propagate in all directions. And even if there is a barrier, it can simply cross the barrier and it can go to. For example, you can easily get the noise or voice from the other room to this another here inside in another room. So that is simple logic. But when you go high frequencies towards a light, high frequencies like terahertz or thousands of terahertz, the wave always travel in a straight line. And if there is a barrier, it will be reflected back. So this already we discussed in very similar concepts. So this one is very difficult to guide or difficult to manage. So for that we are introducing structures which can carry the high frequency signals in a particular fashion from place A to B. For this, various shapes were introduced. One is the best known coaxial cable and two wire lines. If you see most of the old type telephone cables, there you will see two wires which will be uh, connected by plastic material, and both will be having exact same distance through that, which we call two wire line. Uh, then the most very well used planar type structures like microstrip lines or PCB board, where you have metal on both top and bottom separated by a dielectric material. So, and other than that, we already have seen the waveguides. So these are the four possible most common transmission lines, and these transmission lines will be having field distributions inside that will be very useful for understanding how the wave propagation takes place. Now, in early about 100 years before, I think in 1910 or even before that period, both there is a big problem between this wired transmission lines and wireless conditions. They were been evolving, and so at that time, the telephone cables were used almost everywhere. I think in 1902, 1905, like that, in this period. Okay, so there was a big problem that the crosstalks as well as slowing down of the voice signals and sometimes fade away. All these concepts were being studied over the period, and they understood that the frequency is largely influencing the transmission behavior of the wires. So that is why they treated those lines as a separate line. They will be called as transmission lines. These transmission lines are far different from the regular wires, which is used for carrying the currents, electrical currents for for home and other appliances. Um, so this transmission line theory is completely different. These are applicable only for high frequency signals, where actually after the low frequency signals like voices and everything will be modulated to high frequency. That high frequency signal will be traveling over this transmission line, and this been studied by many people, and there are some theoretical derivations were being developed by many people. One of the finest works was were being done by Oliver Heaviside, one of the important person in the electromagnetic field theory. In fact, the present day what you call syllabus for the electromagnetic field theory as well as transmission line theory originally been developed by Oliver Heaviside, and he developed several important concepts which we use nowadays like impedance, admittance, immittance, then so-called open circuit, short circuit. All these things were been originally developed by Oliver Heaviside. In fact, many people do not know about his name, so that is why I put his photo here, and you people at least should remember his name in future at least. So Oliver Heaviside understood this problem. He studied with several experiments. When he applied high frequency signal to a wire, he always found interesting concepts, particularly when he studied the reflection coefficient. We already know what is reflection coefficient. This is going to tell about the reflected signal divided by the incident one. So which we can say, let's say there is a voltage signal which has positive along the z-axis and the minus, and here it is the incident wave along the z-axis. So along the z direction, when the wave is traveling, some signal will go inside, some signal will be reflected back. So when he studied this with respect to various frequency signals, he found that in some frequency cases only he got the very low reflection coefficient, which means that the signal will travel from the source up to the load, and some cases it is almost equal to 1. The reflection coefficient is equal to 1 means no signal is getting inside, simply whatever the incident wave simply get reflected. So this is completely frequency dependent behavior. So this is very important moment in the in fact in the history of electronics and communication engineering itself, that the transmission line has a frequency dependent behavior. And this is completely resistor. There is no RLC. Source is also a resistor. Therefore, this behavior is supposed to be happen because of this transmission line, which is not simply the resistor. There's some plus reactance term supposed to be there. In fact, the reactance term itself introduced by Oliver Heaviside. So this reactance term supposed to be we already know only two things. One is capacitor and inductor. So these two behaviors are available in the transmission line, and there comes the new term. Instead of resistance, he started to introduce the so-called the impedance, and this impedance is R plus jx. So this reactance is coming into the picture. This reactance, he told, it is purely depends on the length of the line and the architecture, the structure of the so-called the guiding or the transmission line. So this is what the initial point. So where the reflection being understood, and as well as the way they travel and reflect back. And the another very crucial thing is the delay. So many people understood that the high frequency signal travels in the velocity of light, but when it travels in a medium like this, it travels very slow. So that is why they introduced a new factor called u, which is we call phase velocity, and which is actually always be treated as the velocity of light with respect to the beta. The phase constant also being introduced at that particular point. So this is how the transmission line theory have been evolved. So obviously we are supposed to give a equivalent circuit for the transmission line, and that is where the modeling of transmission line theory, transmission lines have been evolved. And the genius of Oliver Heaviside is very important. He told if it is for every length, let's say I am having length 1 meter, if it is giving one LNC value, and if I increase to 2 meters, it is going to give another LNC value. Therefore, it is completely length dependent. So we are supposed to divide this all these length of the lines into small portions, which often referred with del z. So for each del z, we are going to have all these LC elements along with other elements like R and G. G is nothing but the conductance. So this four coefficients supposed to be calculated for this small distance. So whenever we vary with respect to length, we can easily put them in series and parallel. We can easily calculate all the value. And this another way genius is we need not to worry about the complicated Maxwell's equations to be solved, because we already know we have great knowledge about this RLC equivalent as well as the RLC elements, how to solve for a given network. So with that simple simple circuit theory, we can easily solve the transmission line theory. So that is what the idea of Oliver Heaviside. He was very much successful in that way. So that is why he introduced resistor, capacitor, inductor, and the conductance. These four elements he introduced for a small length of line. And this he called as the distributed elements. You should remember the normal capacitor, inductor often referred as lumped elements, and these elements are distributed over the length. So that is why they will be called as distributed elements. So hereafter I will say these elements as a distributed elements. And more importantly, these famous structures like coaxial structure or two wire lines, these kind of parallel plate structures, all these things, for this we already calculated the inductance and capacitance. The other two things are nothing but the resistance and conductance, where we can simply apply the electromagnetic theory and we can easily derive that. So this derivations are available in some of the important books of transmission line theories, like not in SEDIQ, but in other books it is available. So here it is given with all the values. These values will be given in terms of the ohm per meter or Henry per meter, like that. So to tell that they are actually highly depends on the distance where the wave travels over. So so this is how it will be represented, and these are called the secondary parameters of the transmission lines. Primary parameters, of course, nothing but alpha, gamma, beta, and gamma, like that. So now the challenging part is this wave propagation and these distributed elements, which we call RLGC, supposed to be connected. And interestingly, these equations are valid only for high frequency signals alone. When you give low frequency signal, the same coaxial cable will behave completely in different way. So that is you have to keep in mind. And we supposed to include, in order to calculate this R and G, they have introduced the skin depth as well, which is highly depends on the frequency term. When this frequency is very, very high, skin depth will be very, it will be very low. Okay, so therefore the resistance and the conductance behavior will completely change. Of course, the inductance and capacitance also will change. So this is how the basic experiments were used to model the transmission lines. And so now we have to derive the expression for the wave equations using this RLC equivalence. That is where the important concept being evolved. So for this, Oliver Heaviside has come up with the simple idea that over the small length of line in the transmission line along the z direction, a small section will be having equivalence of the distributed elements, often given with the incoming current, and there is a parallel voltage, and this voltage will vary over the period. Okay, because when the wave is actually traveling like that, everywhere actually it is going to vary. So that is why it will be given with V of Z and T, which means that with respect to with respect to space and time, it is going to vary, and this is also applicable for the current as well. Now, with respect to this V and I, the ratio will give the impedance. We already know that Z is nothing but the complex ratio of voltage and currents. Okay, and they are going to give the rise to the expression for the resistance, inductance, capacitance, and the conductance, and they are multiplied with del Z. So for a small distance, these values are calculated, and this will travel like that. So the same element will be keep on repeating, which we call as the distributed elements. Now, for the single small section, we can easily calculate the voltage across the transmission line with respect to the current. So which is given with a simple equation, and the next, this is the next after this, the voltage which is available. So this is where the let's say there is a voltage here at Z plus del Z like that. So this voltage depends on this, therefore this voltage will be depends on this voltage, like that they are connected. The same equation we can write for the current. When you write for the current, you will get in terms of G and C will come. So these two equations we supposed to solve for when the del Z value is very, very small, then only we can have the very precise one. For this, people always used to normalize with respect to del Z. So how to normalize with respect to del Z? It is very simple. You have to divide the entire equation by del Z. So you will get del Z here. Here it will be cancelled, and this you can simply ignore because this is going to be limited within the del Z itself. Here this equation will become Vz itself, which is anyway it is going to be the same. So there is no logic in that. Once you have done it, when you put or when you make the value tend to 0, this value will become maximum because it is in the denominator. This value cannot be 0, but this value is supposed to be the maximum possible, which means it is not possible to have infinite value, but the maximum value which is given as a input. Same thing we can do for current as well. So you got these two equations. So this equation, I believe you can see that there is a differential operator naturally comes into the picture, which comes with one side space, another side with time. So this is the perfect setup for the wave equation supposed to be derived. So hereafter we have to go for the second order differentiation. So when you take for the second order differentiation with respect to Z, then you can substitute both the values on the other side. So what we are going to do, we are going to say that the voltage and the current we are going to represent as a function of the source and as well as the function of the time. So where the omega is coming to the picture, the omega is nothing but 2 pi f, which means only one particular frequency signal is traveling inside the transmission line. So now we got these two equations. Now we have to substitute this equation here and this equation here, which we call self-consistent solutions. and thereby we can easily get it. So we got these two equations, and since it is a exponential function, after differentiation with respect to time, the same equation is going to come. So this is going to be again the same. So that is why it is represented as Is and Vs itself. So now we got simple equation. This we have to solve. So just differentiate this, and by dou z, then you can easily apply this equation and you will get the answer. So when you put these two equations, and you will get a new expression for voltage. Same thing for current also we will get, which will give this equation. In fact, for current also you will get the same expression, and so you can have the wave equation. So we got the wave equation. We know that the second term in the wave equation is going to be a constant, a linear constant, which describe the propagation behavior, which we call propagation constant, which is often represented by alpha and beta, which is nothing but root of this r plus j omega L into g plus j omega c. The interesting thing is all the wave propagation constants like alpha and beta are now represented in terms of RLC equivalence. This is what we want. So now we can see when we characterize a transmission line in terms of RLC equivalence, we can even describe the wave propagation behavior also in the same way. Now we can have the solution for this equation. So the solution for this equation, we already know about that. There will be two solutions, and one solution describes the wave traveling in the forward direction, another one traveling in the reverse direction. You're supposed to remember the forward going signal will be represented by minus omega z, because this minus term is coming to the picture. So that is the forward one. The reverse one will be having plus. In order to define the magnitude for the positive forward going, the positive term will come, the negative term will come for reverse. So this is nothing but the reflected component. This is going to be the incident component, like that you can treat. Same thing applicable to current also. Now we are going to substitute this expression in the initial representations. By the way, we can have the so-called the expression for voltage and current will come. So that is going to be the incident component, and the forward traveling behavior with alpha. The alpha is purely depends on the resistance and conductance, and the beta is going to be depends on the L and C value, and with respect to time and space it is traveling. It can be also treated with sine term. There is no big problem because we have only exponential term. Now considering this real part, it is taken with the cos term. Now we got the wave equation where alpha and beta also can be expressed in terms of RLGC. The next one is the wave impedance. We already know the wave impedance for a lossy medium, which is represented by this, and this is the real and imaginary term. This is the phasor expression. Now we have to get the same wave impedance for the transmission line. So the wave impedance for the transmission line, we can simply state as two possible way: the incident wave, incident voltage divided by the incident current. Same thing for minus, because it is traveling in the opposite direction, where the voltage for the negative side as well. So this is supposed to be substituted. So we have the equation here, and just we have to separate this positive term, negative term, and just we have to divide. You're supposed to remember that this term and this term is going to be the same for voltage as well. So they will be simply cancelled, and you will get only the remaining term like this, where this is going to give this and this is going to give this. And now we need to get, this means that the wave impedance has two solutions. Like this we have two solutions, and these two solutions supposed to be combined as a single solution. For this, the best way is multiply and take root of formulas. So that is what been done here. So when you multiply, you will get Z0 square, and you will get both the gamma will be cancelled. You will get numerator and denominator, and the square one will be taken to the other side. You will get this. So that is what we call the wave impedance. So this is the wave impedance of the particular transmission line of a medium. So you're supposed to remember that throughout the z direction, this is going to be the ground, and this is going to be the conductor. So this fashion, even this distance between the wire and this, or everything is supposed to be constant. If there is some undulations or something, then we can't apply this characteristics impedance going to be the same. It may be up to here, it is characteristics impedance, it is some other impedance. You're supposed to remember that. So this is the characteristics impedance of the transmission line. So now we got almost all the important constants of the wave which is traveling in the transmission line. So which we call as a primary term as alpha, beta and the gamma, which means eta. These are the three primary constants, and the secondary constants are nothing but RL, GC. These are the secondary components. So all these components are now literally connected. Now for any transmission line case, we can easily solve this. Now there is a special case, of course. So that is, one is lossless transmission line. So lossless transmission line is, which means that its conductivity, particularly the which is made up of perfect conductor, where the conductivity is 0, as well as there is no skin effect. So considering these two, we will assume that the conductivity is 0, which will give R and G will be equal to 0. If R and G is equal to 0, then we can substitute here. This R and G value will go down, and you will get omega term alone will come. This also will be cancelled, which means you will get purely L and C combination will come. So the impedance will be purely reactive. Okay, like that you will easily get it. And then what about the phase constant? The phase constant will give alpha and B, where when you cancel this two value, you are going to multiply this. You will get omega j omega square, L and C will come. J omega you can take it out, and root of L and C. And so this is what the very important expression, which clearly tells that any transmission line, including the lossless transmission line, also completely resonating structure. When this value equal to 1, then you can easily get the frequency. I believe you can easily understand this beta. When it is equal to 1, then you will get omega root LC will come, where you can say that it will happen at only one particular frequency, which is nothing but 1 by 2 pi root LC. I believe this is very familiar equation for defining the resonant frequency of any particular structure or any particular RLC combination, and which also defines the phase velocity. So this phase velocity describes this value. When this beta value is greater than 1, obviously, which clearly tells that this phase velocity is not equal to the wave, which we call the velocity of light. Obviously, we will be getting different speed inside the transmission line. So it is going to be slow all the time. So this is what the things we can understand from the lossless transmission line. And another interesting transmission line behavior is there, that is called distortionless transmission line. First of all, we have to understand what is this distortion is. That for instance, you have the spectrum. Okay, in this you have different frequency signals are traveling in a transmission line. Assume that there is a transmission line, in that different frequency signals are traveling. Okay, different frequencies are traveling, and these all going to follow same type of wave propagation behavior. There is no big difference. Okay, and the phase velocity u will be applicable to everything, everywhere the same. Okay, so if the phase velocity is going to be same, and which is completely depends on beta, the beta is again highly depends on the frequency. So when the frequency keep on changes, then the beta will change, the phase velocity will be different. So each and every frequency component will travel in different phase velocities. Let's say you have a particular information. This information is available in a broadband. Okay, so the broadband information, one signal broadband means the same information is, let's say 0, 1, 0, 1. They are actually given to different frequency components. Simultaneously, they are transmitted. So that is why parallel communication takes place. Your speed of communication is very, very fast. But the problem is all these signal will not arrive the destination at the same time. So we supposed to wait for a moment to receive all the signals, and in fact we supposed to use complicated circuit here. So this makes a dispersion or distortion in the symbol. the symbol whichever is having, let's say this is the signal, but later of a particular period this will be distorted, and so this same expression is elongated. So this elongation leads to several issues, both in circuit level for the receiver side as well as in the transmitter side. Both the side it will be a problem, and it is very difficult to manage such a large frequency signal simultaneously in the. This is actually one reason that if you, I'm not sure whether how many of you know this, this Volt-on-Tape cable TV problem will come. Like they will be having the same this. You can see many whenever people see sports, that two sports channel will come in the same screen itself, which we call ghost signal. So crossover of the frequency signals, everything will take place. This is a big problem in the due to the distortion. So how to avoid the distortion? In order to avoid the distortion, we're supposed to manage the phase velocity. So how to manage the phase velocity? It's supposed to be linearly proportional to the frequency. It should not be non-linear proportional. So to make it, we need the phase constant supposed to be linear to the frequency. So that is what the expectation to get the distortionless transmission line. So to make it, this I'm telling, this is 100 years before this argument has been raised. So that is originally solved by Heaviside, and this condition been often referred as Heaviside condition. So Heaviside condition is simple, that you substitute R by L, which is equal to G by C. So in some books you can see that it will be mentioned as RC equal to GL. So both are same only. So this is the condition. So when you substitute this condition into the phase constant and the impedance, you will get some interesting solutions. First of all, we have to apply to the phase this propagation constant, which is alpha plus j beta. So when you substitute, so how to substitute this to, which is very simple. You are going to take this R by L and G by C outside, and by the way, you can easily get it all. So for this R by L, you have to, so this L component and C component is taken out. So you will get R by G, something like this. So you can see that these equations are rearranged, and we get this equation. Now R and L will be said as equal to GL. So everything will be oriented with RL itself. The G concept is removed here. So by the way, you can represent everything with RLC itself, and which is nothing but this is alpha, this is nothing but beta. So this alpha and beta, which is given here, you can see that this beta is nothing but 2 pi f root LC. So f is linearly proportional. The constant is nothing but 2 pi root LC. That is the constant, and so that is how the linearity is maintained for the beta. So this is more than sufficient. Added advantage of this particular condition is you will get alpha independent of frequency. There is no omega term here, or there is no frequency term here. So you will get almost constant attenuation throughout the spectrum of the frequency. So it is expected a distortion-free transmission line, supposed to hold this, the beta and this alpha. So that is what it is expected. The problem is that given transmission line may not show this such a beta value linear over the long spectrum. Let's say this is actually 2 gigahertz, 3 gigahertz, 10 gigahertz when it comes into the picture. So different transmission line will show different behavior. So for instance, when you take the waveguide, which we have seen in the last class itself, the imaginary part of the gamma, which is nothing but the beta, which is actually calculated using a simulator, and from here onwards the propagation start, but the propagation is not linear up to this, but it is start to become linear after certain frequency range, which here it is approximately 8 gigahertz to 12 gigahertz, which we call the linear region. And this linear region often referred with a name called useful region, where the distortion free transmission could be possible. So here you can see the linearity. This is for a rectangular waveguide. But if you take the normal PCB is nothing but there is a dielectric material, and it is actually coated by metal on both sides. So this type of structure when we simulate, so here you can see port 1 and port 2 I kept, and the wave is traveling from here to here. And so using this wave propagation, this imaginary part of gamma is calculated, which we often refer as microstrip line. We can see that the beta is almost constantly keep on increasing. This means it is linearly proportional, which is expected like this. So this is one important reason that even for low frequencies like megahertz and gigahertz and up to tens of gigahertz, even beyond the scope of very high frequency signals, this transmission line, this PCB based transmission line or microstrip line, is one of the most successful one. So this is one of the important reason you could see that this particular structure PCB is used for low frequency radios, like of course for what we call the FM radio. You can see that it is mostly made up of PCB based structures. And high frequency antennas, your mobile phone which is operating at gigahertz, your laptop is working in almost purely in gigahertz. And even very high frequency signals like radars and many things, actually they can be supported with this transmission lines itself. Maybe in the future I will say how to use it, but this is the basic idea. Okay, that is how the distortion free transmission line could be achieved, as well as and applicable with minor loss will be available. So that is something sacrificable. And in summary, we can get say that the transmission line is modeled into distributed RL GC elements, which we call distributed element. And by this, we can get a equation for voltage and current. From that, we got the wave equation. The solutions were being arrived, where this alpha and beta characteristics impedance, RL, GC, everything is connected. So that is we call primary and secondary constants of the transmission lines, which is summarized here. This is a general equation for propagation constant and the characteristics impedance or the wave impedance. And for lossless and distortionless line, there are some special cases which are longly needed, but lossless is almost impossible to make, but distortion is very much possible with reasonable alpha, which is a constant one, as well as the beta, which is a linear proportional with the frequency. That is, this is in fact one of the important reason that when they make the coaxial cable or PCB or two-wire transmissions or waveguide, everything, they will be using this distortion-free condition to get the to construct such a complicated, so not complicated, to make such a correct transmission line. Okay, so we can't randomly fabricate the structures. Everything needs a little bit proper engineering, and this where the distortionless conditions are coming into the picture. And simple example we can take, there is a air line. Air line is nothing but simple two lines which is actually placed in a air medium with a constant distance throughout the z. Okay, along the traveling direction, this will be maintained properly, and which has the characteristics impedance and the phase constant. Phase constant is beta is given, at frequency is given. So this frequency is also given. Once the frequency is given, we can easily calculate omega, that you know that. So now we have to calculate the inductance and the capacitance per meter for this line. So it is given as there is no value of alpha. So if the value of alpha is not given, you can very well assume that is a lossless. Since it is a lossless, obviously R and G is going to be 0. So that is what it is described here. R and G is 0 because alpha is not given. And since it is a air medium one, there is no exchange of fields here. So potential drop will be constant. That is why it is assumed as alpha is 0. Okay, so we can easily use these two equations to calculate that. So one is having root of LC, another one is having root LC. So when you multiply these two equations, you will get L. When you divide these two equations, you will get capacitance. And the frequency, we already know the value. So that is what it is done here. So first one, we are going to take Z0 by omega. Z0 in many books, it will be mentioned as R0. So you should not confuse that. So best you use always Z0 itself. So this also you use Z0 by beta. So when you divide, you will get capacitance where frequency is coming to the picture. When you multiply, you will get the L value will come. Okay, so that's all. So capacitance and inductance are calculated in terms of given values beta, Z0 and the frequency. So we are going to substitute all the values. So here it is calculated. So these all values supposed to be mentioned in terms of units with proper meters or centimeters, depends on the value it is expected. So mostly if it is given in megahertz, it will be come in terms of meters. When it is given in terms of gigahertz or something, it will come in centimeters. Otherwise this value will become little lesser values will come. So that is why. And here there is a example which is given in this. Here you can see the frequency, Z0 value, alpha, beta is given. Now you have to calculate all these values. For this you have to use the general expression, which is very simple one. The answers given here. So you also try. I will give the solutions maybe in another tutorial class or something. Here is another example. So Z0 is given alpha, and interestingly the u value is given, which is phase velocity, and then we have to calculate this RL, GC, and the lambda we have to calculate. The lambda, which we imagine that we can simply calculate by C by F like that, which we can't use this inside the transmission line because the velocity is not same. So we're supposed to use this special u value at this frequency. So for this we are going to here the given clue is distortionless line. Since it is a distortionless line, we are going to use this expression, and this expression was reduced. So for a distortionless line, Z0 value is well known, and this RL GC value. So by the way, you will get this resistance and the characteristics impedance. Of course, it is very well known, where it is made up of L and C, where the two values are not known. So we have to calculate that. So first we are calculating the R value. This R value, alpha and Z0 value, both the values are known. Z0 is known, alpha is known. So we can easily calculate the value, which is calculated in terms of that. Next we are using this u. U is nothing but 2 pi f divided by beta, which is nothing but 1 by root LC, which is applicable for the distortionless line. So here we can easily compare with Z0. So u is equal to this Z0. So when you multiply this, you will get L, and when you divide, you will get the C value. So by the way, R, L and G, C, all the values are calculated. These values are clearly given with all the set of equations. I believe you can easily understand that. Finally, we are calculating the lambda, which is nothing but not C by F, it is U by F. Substitute all the expressions, you will get the wavelength. So this is often referred in most of the books with G, which means guided wavelength. So the guided wavelength is completely different from the free space wavelength. Free space wavelength will be defined as lambda naught. Okay. So the ratio between them is nothing but the beta itself. And you can see the telephone cable line with different. This actually all the values are somewhat realistic values, which are used for the high frequencies signals, but it is given for low frequency signals itself. So I'm stopping here now. If you have any questions or something, you can very well ask.